What is up, hello gangsters and Jake Paulers? Welcome back to another Physics 2 lab. In this lab, Lab 2, we are going to be once again revisiting the charged tape repulsion problem, this time using a new model to calculate a new, more accurate estimate for what the charges on a piece of tape would have to be to levitate one piece of tape above another. And here is this new value for a charge that we are going to find. We'll come back to this later. Once again, just like last lab, we are going to be mainly using Coulomb's law in this lab, which states that the force that charged particles enact on one another is proportional to the two charges of those two particles and the distance between them, related with some constant. We're not going to be bringing in any new physics ideas into this lab, but we are going to be using a new, different computational model. Now, the actual physical experiment for this lab is the same as the previous lab, and it's where we used two pieces of tape and levitated one piece of tape above the other, assuming that both of these tapes are equally charged. And we, in this case, would view the piece of tape above here as the system and everything else in the picture as the surroundings. But once again, this is just the same physical experiment as in the previous lab. What changed, though, is the computational model that we used to model this system here, where in the previous lab, we assumed that all the charge in these tapes was concentrated at a single point. In this lab, we did not make that assumption. We just assumed that the tape had equal charge and that the charge was evenly distributed amongst them. And we also made the assumption that this system has the initial condition of having that set charge and being at rest. And so this new computational model makes use of a nested loop to compare each piece of charge in the bottom tape and see the force that it creates on each charge in the top tape. So we create two lines of charge where the charge of one piece of tape is evenly distributed among a line of particles, and then we calculate the force of each of those particles on the bottom tape on each of the particles in the top tape using this nested loop. And what we end up finding is that the charge in each tape would be about 33.6 nanocoulombs, or 3.36 times 10 to the negative 8 coulombs. And what's interesting about this outcome is this is actually more than what we estimated the charge would have to be for lab 1, where we assumed that each of the particles, or each of the charged tapes, was just a point particle. And this actually does make sense, and we would assume this lab 2 number would be the more accurate one, because in lab 1, this assumption sort of implicitly says that each bit of charge in the bottom tape is acting on every single bit of charge in the top tape equally, when in reality, a tiny bit of charge might act on the charge directly above it, much like this, but for charges further away, since this charge is more spread out, the force would be weaker because of the distance and also less in the vertical direction. So we would expect to need more charge to hold up that tape than we saw.